Okay, in this chapter, we're going to examine two very important questions. The first is, how do atoms bond together? We know that different atoms can join together in order to form molecules. Two hydrogen atoms can bond together to form an H2 molecule. Two hydrogen atoms can bond with an oxygen atom to form H2O, or water. So how is it that these atoms bond together like that? And then once you've got a bunch of molecules, let's say you've got a bunch of H2Os, a bunch of molecules of water, what keeps the water together? And so we're going to be looking at how atoms bond into molecules and then how those molecules attract one another. There's a lot of content in this chapter, so I really strongly recommend that you really focus on taking good notes. Stop these videos, pause them when you need to take good notes. And of course, if you have any questions, feel free to contact me and ask whatever you're confused about. Okay, so for our two big questions, how do atoms bond together to form molecules, and how do molecules attract one another? What you have to understand is it's all about the electrons. It's all about what the electrons are doing. And so that's what we're really going to focus on this chapter, is what the electrons are doing. Now, we have something called electron dot structures, which are a way of representing the kinds of interactions that electrons can have with one another, and we'll get into that shortly. We'll explain how they work and how they're used to represent chemical bonds. We're going to talk about how ions can form. We'll talk about what an ion is and why they're important. And once you have atoms that form into ions, we'll talk about how ions bond together and form ionic bonds. Now, that's just one way that atoms can bond together in a molecule. There are others, and we're going to talk about some of those, including metallic bonds and covalent bonds. There's even something called a polar covalent bond. And then we're going to talk about molecular polarity and how that relates to molecular attractions. So let's get started. So first of all, we have atoms bond together through their electrons. To learn about bonding, therefore, we need to know something about how the electrons within an atom are organized. Electrons behave as though they are contained within a series of 7 concentric shells. So here we have a picture showing a model of an atom, and you may never have seen this kind of picture of an atom before. Often we see the model of the atom where you have the positively charged nucleus and you have the electrons orbiting the positively charged nucleus as though the nucleus was the sun and the electron was a planet. This is the so-called planetary model of the atom, and it's useful in some contexts for understanding what's going on with an atom, but this is another example of what we call a conceptual model. The actual inside of the atom looks nothing like this, nothing at all like this, but we imagine an atom behaving like this sometimes because it helps us understand things about it. This picture is similar. The actual atom will look absolutely nothing like this. It doesn't have these concentric rings, but it does have these shells. So basically, here's what you need to know. Surrounding the atom are these regions of space, which are called shells. It's not something physical, it's just a particular area of space. And these shells, these areas of space, that's where the electrons are allowed to be. They're not allowed to be in between the shells, they're only allowed to be in the regions where the shells exist. And the main thing about these shells is that each shell is only able to hold a certain number of electrons. So the very first shell around the nucleus of the atom can only hold 2 electrons. Once you've put 2 electrons in that shell, it's completely filled up. It can't hold any more. The next shell can hold 8 electrons. And so it doesn't have to hold 8, it can hold less than 8, but 8 is the maximum. And so once you've filled up the 8th electron in the second shell, the next electron you add to the atom will go to the third shell. And the third shell, it also can only hold 8 electrons, and so on. And so you can see this list of yellow numbers here on each shell. That's telling you how many electrons each next shell can hold. Now, because drawing spheres is more complicated than drawing circles, we usually represent these shells not as spheres, but as circles. So here you see the helium atom here, which has 2 protons and 2 electrons. And so that first shell's got 2 electrons in it, and it is filled up. And so here we have another example, neon. Neon has its shell, its first shell filled up with 2, and its second shell filled up with 8 electrons. Here we see another atom, argon. It's got 2 electrons in its innermost shell, then 8, and then 8 in the outermost shell. Again, its outermost shell is filled because that's the most that the third shell can hold. Now, what's interesting about these 3 elements, helium, neon, and argon, they are members of the same group in the periodic table. Remember, the groups are the vertical columns. And so, what can we say about these members of this group? Well, they're the atoms that all have their outermost shell completely filled. That's why they're all chemically very similar to one another, because they all behave in a similar way. They all have that similarity that their outermost shell is completely filled. And this is, of course, the group of the noble gases, and that's the type of element that doesn't really interact with other elements. It doesn't form molecules. They like to stick to themselves, and the reason they like to stick to themselves is because their electron shells are completely full. So our key here, each atom has its own configuration of electrons, and elements in the same group have similar configurations. That's why they have similar physical and chemical properties. Now, one thing that's worth mentioning, the outermost electrons, those are the only ones that can ever be involved in chemical reactions. And so the outermost shell, whether it would be this shell in this atom, that would be the outermost shell because there's only one. Here, this shell would be the outermost shell. The next atom up on the periodic table after argon would have another third shell because we'd be adding an electron. Only the outermost shell is involved in these kinds of chemical reactions, and so that outermost shell has a special name. We call the electrons in the outermost shell valence electrons because and it's the valence electrons that are involved in chemical reactions. So just to recap, if we're talking about valence electrons, we mean the electrons in the outermost shell of an atom, and these are the ones that can participate in chemical bonding. Now we can use a standardized chemical notation called electron dot structure, which shows the valence electrons surrounding the atomic symbol. So here is an example of electron dot structures. We have a couple of different atoms here. We've got chlorine and we have carbon. So let's take chlorine, for example. This is the chemical symbol for chlorine, and then we see 1, 2, 3, 4, 5, 6, 7 dots surrounding chlorine, and that is showing that chlorine has 7 electrons in its valence shell. Now, of course, there are other electrons inside in the inner shells, but in the outermost shell, this is how many electrons chlorine has. Now, one of the things that you can notice in the picture here is that they've grouped these electrons together and they said, okay, these two are what they call paired electrons, these two are paired, these two are paired, and then you got this one unpaired is just hanging out by itself. It's actually the unpaired electrons in the valence shell that are available to participate in chemical reactions. Now, over here in carbon, we have 4 different unpaired electrons. And as to why electrons sometimes pair up and sometimes don't pair up, that's a little bit beyond the scope of this class, but you can just accept the fact that they do, that this is something that happens in chemistry. And the conditions that cause them to pair up or not pair up, that affects how these different chemicals, or how rather these different elements, can participate in chemical reactions. And so chlorine has 1 unpaired electron, and so it can only actually form 1 bond with another atom, whereas carbon has 4 unpaired electrons, and so carbon can actually form 4 different bonds. So for example, with chlorine, we've already talked about NaCl, there's one unpaired electron that's available for bonding, and so it can bond to one atom. So one chlorine atom can bond to one sodium atom and make sodium chloride. Carbon has four unpaired electrons, so it can actually make four bonds. So as an example, we might look at methane, which has a chemical formula CH4. Four different hydrogen atoms can bond to one carbon atom because there's four unpaired electrons in the outermost valence shell. And for completeness, let me write that down. This is methane, of course. And this is sodium chloride, which of course we know is just salt. But the key thing that you need to know is that it's the unpaired electrons that are involved in the chemical bonding, and the number of unpaired electrons that exist in the valence shell, that tells you how many chemical bonds that element can form. And by the way, we saw in one of the previous slides that some of the really far away shells can hold lots and lots of electrons. You don't try to draw all of those. And so typically, here's an example of krypton, which has 18 valence electron. We don't try to fit 18 different dots into this picture. We just draw the 8 that are the farthest away from the nucleus, and we use that to depict it in this kind of notation. Remember, this notation is called the electron dot structures, obviously because we're representing the electrons, the valence electrons, as these little dots here. Now, something that's really interesting, we've talked a lot about the periodic table, but why does a periodic table look the way it looks? Why do elements organize themselves the way that the periodic table shows us that they are organized? The answer has to do with this shell structure. So let's just look at some of the elements on the periodic table and look at how many unpaired valence electrons they have available. We start with hydrogen, which has one proton and one electron. So there's one electron in its outermost shell, and that is hydrogen. Then we go up to the next element, which is helium, which has two protons and two electrons. And we know that in that first shell, 2 is the maximum number of electrons that you can possibly have. So that shell is absolutely filled. So the next element up is lithium, which has 3. It's got 2 in the inner shell and then 1 in its outer shell. But look, lithium and hydrogen, they both have one unpaired electron in their outer shell. Okay? Now if we keep adding protons to get new elements, the next element up is beryllium, and then we can go down the periodic table. There's carbon, which we've seen has 4 unpaired electrons. We have oxygen here, all the way up to neon, which again, all 8 are filled, so you can't add more electrons in that shell. So the next element up has to make a new shell. It's got 1 extra electron in it, but hey, look, sodium, that's what Na stands for, lithium, hydrogen, they all have 1 unpaired electron in its outermost shell. These guys over here on the right, they all have their shells completely filled. So once you get a shell completely filled, you go to the next row on the periodic table. And so remember, these rows are called periods. Each period is caused when the electron shell is completely filled, and then you add 1 more electron that brings it to the next period. Now we know that the groups, that's the vertical columns are the groups, they all behave chemically similarly. The reason why is because they all have that same electron configuration in their outermost shell. All of the elements in this group have 1 unpaired electron that can be used to form chemical bonds. Over here, all of the elements in this group have 4 unpaired electrons with which they can form chemical bonds. Over here, the so-called noble gases, their shells are completely filled. They have no unpaired electrons. They can't form any chemical bonds. So, this explains why the periodic table behaves the way it does. Both the behavior of the periods, as you go from left to right, and also the behavior of the groups as you go up and down. Okay, let's do a check our understanding kind of a deal. Let's consider the element sodium, which has the atomic number 11. It has only one valence electron. If it were to lose this electron, what other atom in the periodic table does the sodium atom then resemble? And our options are neon, which has an atomic number of 10, that is 10 protons, 10 electrons, magnesium, which has an atomic number of 12, lithium, which has an atomic number of 3, or is the answer sodium can only resemble sodium? Those are our options. What do you think? Pause the video, make your best guess. Which one do you think it is? Okay, so let's see if we can reason it out. Let's look at the periodic table. So we're talking about sodium, which is over here on the left. It's got one unpaired electron, and so if it were to lose that electron, then it would be, it would have basically the completely filled shell. In other words, okay, let's consider sodium. We know that sodium has 2 electrons in its innermost shell, and then in the next shell it has 8. So it would have 1, 2, 3, 4, 5, 6, 7, 8, and that would give you 10 electrons total. The next element up would have 11 protons and 11 electrons. That would be sodium. And so sodium has this one extra electron. Now, if that electron were to be thrown away, if it were to be ripped off or something, then you would have only the electrons underneath it in the lower shells. And that would start to look a lot like neon, because neon has 2 in its inner shell, and then it has 8 in its outer shell. It's completely filled. And indeed, that is our answer. The answer is A. It would most resemble neon, which has 10 electrons. And so remember, it's the electrons that define your chemical properties. But, and it's a big but, there's a huge difference between neon and sodium missing one electron. Do you know what that difference is? The difference is this. Neon still has a proton for every electron. It's got 10 protons and 10 electrons. But sodium, that's missing an electron, it has 11 protons and only 10 electrons. So neon has all of its charge balanced. In other words, for every positive, there's a negative. But for sodium, that's no longer true, because if you take that outermost electron off, then it's missing a negative charge and it has an extra positive charge. And that's going to be important for understanding how sodium can bond with other elements. Now let's talk about sodium a little bit more closely, and we want to do so in the context of what happens when it does lose that outermost electron. So here we have sodium as a normal atom, and so you can see it's got its electron with a positive 11 charge because there are 11 protons in there. And then there's the 2 electrons paired up in the innermost shell. We have 8 electrons in the second shell, so that shell is completely full. And then we have this one extra guy here in the third shell, that one extra electron. If you were to rip this extra electron away, it would be gone, and what you would have would be the electrons with 2 in the inner shell, 8 in the outer shell, and that would give you a total of 10 electrons, but you'd still have 11 protons in the nucleus, and so that would give you a +1 net charge, the charge of one extra proton. And so for the regular sodium atom, we say that it is electrically neutral because the positive charges of the protons cancel the negative charges in the electrons and vice versa. But here, there's an excess of protons in that sodium with the electron ripped off, and so there's a positive charge. And we have a word for atoms that have either gained or lost electrons. We call those atoms ions. And so if you hear ions, an ion is an atom that has been charged either by having extra electrons put on it or some electrons taken away. Now, just a couple more things to mention. One, you can note that here we've listed this atom as just regular sodium. And here we see a little 1 plus indicating that there's a +1 positive charge. And when you see this Na with the 1 plus, that tells you that the sodium has been ionized. In other words, it's been formed into an ion. It's missing an electron. And by the way, some atoms, it's easier to take away their electrons or to add electrons to them. And again, that has to do with this kind of structure. Here's a good rule of thumb. Atoms are really happy when their outermost shells are completely filled. And so if I look at the regular sodium atom, it's got one extra guy here in this third shell. It's going to take 7 more electrons to completely fill this shell. But if instead I rip it away, then what I'm left with is an atom whose shells are all completely filled. And so that's, just a good rule to think about, good rule of thumb to think about, that electrons want their outermost shells to be filled. It's something that when you kind of want to analyze whether something is a favorable or easier thing for an atom to do, if that thing makes their electron shells be filled, the atom's going to be inclined to want to do that. Here's another example, fluorine. So fluorine has got 9 protons and 9 electrons. And so if we count up, we can see the innermost shell has 2, and then we've got 1, 2, 3, 4, 5, 6, 7. We're missing that last electron. In other words, if fluorine could get 1 more electron, its outermost shell would be completely filled. Because remember, the outermost shell, the second shell can only hold 8. So that's something that fluorine is happy to do. So it's possible for fluorine to pick up an extra electron. But what happens when fluorine picks up an extra electron? It gets an extra negative charge because there's 9 protons, 10 electrons, that means 1 net negative charge. And you can see that this is the F1 minus label here telling you that that's a negative ion with 1 extra electron. And again, this whole process is about forming ions. And so we can form an ion of an element by either adding electrons to its atoms or taking electrons away from its atoms. And so these would be atomic ions. It's also possible to create what are called molecular ions. And these are typically formed by the loss or the gain of a hydrogen ion. So not just moving an electron around, but moving an actual hydrogen ion. Now, what is this H+? A hydrogen atom is 1 proton and 1 electron. If you rip the electron off and take it away, then you're left with just that 1 proton, which is positive, and that would be a hydrogen ion. Now let's say you have something like H2O here. This hydrogen ion can actually bond to the H2O and form something new. Here we have some water in which there are some hydrogen ions moving about, and as the hydrogen ions get closer, the hydrogen ion can actually bond with the water molecule to form something new called the hydronium ion. Now, the H2O part, the water, is electrically neutral, but it's this hydrogen ion which turns the whole thing positive. So the hydronium ion would have a positive charge, and we could actually write this out as its chemical formula. That would be H3O and then a plus to let us know that it's positive. Okay, so we have, just to recap, an ion is an atom that has lost or gained one or more electrons. So it's either become negatively charged or positively charged because of the loss or the addition of electrons. Now, when that happens, the atom becomes charged. It's an ion. Ions are charged. And you guys probably remember from your grade school science classes that charges can attract or repel one another. You know that like charges, that would be two positive charges or two negative charges, they're going to repel one another. But if you have two opposite charges, a plus and a minus, those are going to attract. And so if I have a particular element that likes to gain electrons, and that causes it to become negatively charged, and have another element that likes to lose electrons, which causes it to become positively charged, those oppositely charged ions are going to attract one another. And when they do, they can actually cause those atoms to form a strong bond with each other, and we call that kind of bond an ionic bond. The ionic bond is a joining of atoms, or actually specifically a joining of ions, due to the electrical force of attraction between those oppositely charged ions. So the two examples we've seen so far, we've got sodium, which can form positive ions, and fluorine, which can form negative ions. Those two ions are oppositely charged, so they're going to attract, and they can actually form a chemical bond that holds them together just by the attraction of those opposite charges. So let's look at another example. Here's a question. What is the chemical formula for a compound made of aluminum ions, that is Al3 plus? That means there's three extra positive charges, so aluminum has lost three electrons, and O2 minus. So that means there's two extra electrons or two extra negative charges, and so the oxygen has gained two electrons. Now, I can't simply pair them one to one like that, because what you end up with would not be balanced in charge. That's the rule. When the ionic bond forms, a positive is going to be attracted to a negative and vice versa. You can't have this, because there would be 3 combining with the minus 2, the plus 3 and the minus 2. That's not going to cancel out. Now, what about option B? 3 aluminum ions combined with 2 oxygen ions. Well, if I've got 3 aluminum ions, that's going to have 3 times 3, that would give me 9 positive charges, and I'd have O2, 2 oxygen ions, 2 times 2 would give me 4. There's no way that 9 can balance with 4, so that's not going to work. What about this? I'd have 2 aluminum ions, so that would be 2 of this with 3 positive charges each, so that would be plus 6 positive charge. And then I would have 3 oxygen ions, and so that would be 3 oxygens each with negative 2. That would give me minus 6. So here I'd have a plus 6 charge, here I'd have a minus 6 charge, so this one is one that can work. What about this last one? Well, obviously it's not going to work, because 6 times 3 would be 18, and 6 times 2 is 12, so there's no way that they could balance. This one is the only one that could balance. And so this would be our answer, Al2O3, because the 2 aluminum atoms would give us a positive 6 charge, and the 3 oxygen ions would give us a negative 6 charge, and we know that positive 6 plus negative 6 cancels back to 0. And we can actually see the structure of this. We have an aluminum ion and an oxygen atom, and 2 aluminum ions are going to bond with 3 oxygen ions in the kind of structure that you can see here. Okay, so here's another example we can look at. What is the chemical formula for a compound made of magnesium ions? So this is Mg2+. That means it's missing 2 electrons, so it's got a net positive charge of 2. And 2 oxygen ions, which again has some 2 extra electrons, and so it's got a -2 net charge. And so the possibilities are MgO, Mg2O2, Mg4O4, or any of the above. Now, this one's actually a little bit tricky because in terms of matching the charges up, any of these would work. So you might be tempted to say any of the above. But if you've done your reading in the textbook, you might remember that there's actually a preference for the lower numbers. So when you have multiple possible combinations like this in terms of the charges working out, the answer is going to be the one that is the lowest. And so MgO is our answer. And so if we look at this, we have the explanation. The chemical formula is used to show the ratio by which the atoms combine, and by convention, the lowest numbers are preferred. So 1 to 1, that means 1 magnesium atom and 1 oxygen atom, or rather ions, 1 magnesium ion and 1 oxygen ion, is going to be preferred to having 2 of each or 3 of each. By the way, it says here, the numeral 1, however, is implied when no subscript is written. That just means this is really Mg1 and O1, but we don't write the 1 because it's obvious that there's only one of them. But if it were MgO2, that would have to have the 2. You wouldn't write Mg1O2, you'd just say MgO2. But of course, that's not what actually happens. What actually happens is MgO. Okay, so just to remind ourselves of what all this means, we have atoms that have been ionized. They've been formed into ions that have positive charges and negative charges. And those opposite charges create a force of attraction that holds those atoms together. And that force of attraction is called a chemical bond. And so the particular type of chemical bond that we're talking about is what's called an ionic bond, where you have a bond between 2 ions, two atoms that have had either electrons taken away from them to make them into positive ions, or electrons added to them to make them into negative ions. And so each ion has either a positive or a negative charge, which is going to attract and make that chemical bond. In the next video, the next lecture, we're going to be looking at some different ways that atoms can bond together, because there's more than just ionic bonding, there's other forms of bonding as well, but we'll get to that in the next video.